with Maria Bruna speaking now from the University of Oxford. So this is half an hour talk, so we'll have maybe 5 minutes questions at the end.
Yes, thanks so much to the organizers for inviting me to give a talk. So yeah, basically, like I'm going to give this talk is a summary of James' thesis, who just submitted last month, and I supervised together with Rob. So this is like a 25-minute summary of his thesis, pretty much. And I did start my slides with a video of collective behavior and like flux and all this, but I guess as Rob said, like you probably all know, like well, you've seen too many of those, so no longer here. So the plan of the talk, and basically this is really how we led up to these mixtures of active passive particles. That's in the title of the talk. I'm going to first tell you about a system with just passive particles, then a system with only the active particles, and then when we basically put these two things together. And in all of James' work, we considered, I guess, like toy model of these particles and collective behavior, in the sense that we just consider particles on a discrete lattice. Okay, so basically, instead of allowing the positions to be continuous in space, we just fix it on a lattice of spacing h. And then just to fix some ideas on notation. So if you just consider one of such particles, we define the jump rate from a lattice site x to y with this expression here. So if v is 0, we just have symmetric jumps. With the scaling, that's exactly what Rob had in the talk this morning as well. So basically, the symmetric jumps are this d over h square. And they only happen in basically only like neighboring sites. So the spacing has to be h of the jump. And then the thing inside the exponential is the asymmetric part of the jump. And basically, this is chosen such that if you take h to 0, what we want to get is this this drift diffusion equation. Okay, so this is the idea that we'll have this diffusion in the limit as h goes to 0. And of course, you could, well, I think I'm not going to be using this much in the talk, but basically you could get to this by defining the occupancy eta of a lattice site x, and this can only be 0, 1 because we have just one particle. And then basically you can write the master equation for this probability density. Yeah, in this limit h to 0, we get this continuous PD. Okay, this is all very well, but of course what we are interested in is observing things that collective behavior. So what we want is to have many of these particles that move on a lattice and have them interact with each other. And in all of these three models I'll present today, the interactions are always these short-range exclude volume interactions, and the way we model this on the lattice is through an exclusion process. And so again, as like what Rob had, so only like one particle per site is allowed. The rates lambda are still the same. It's only that basically, the rate becomes 0 if there is a particle on that given site. Okay. And so what we're interested in is looking at hydrodynamic limit equations of this process as we take h to 0 and n to infinity. And for this asymmetric simple exclusion process, the PD that you get in the limit is this one here. So there is linear diffusion, and this nonlinearity only arises in the asymmetric part of the jump, even though here also the symmetric jumps are not allowed. Right? So if you remember from so basically like if you have a particle here and a particle here, we don't allow these jumps here as before, like the swapping between two particles. But even with the exclusion in the symmetric part, you get a linear diffusion. Okay? Just to point out, you can actually rigorously find this as a gradient flow of this free energy here, and with this nonlinear mobility. Okay. And in this case, actually, you would obtain, so this is like a rigorous, so the top thing is like a rigorous exact hydrodynamic limit. But if you did a mean field approximation at the level of the master equation, by saying the occupancies of neighboring sites are independent, and you plugged in into the master equation and Taylor expanded, you would get the same nonlinear diffusion equation in the limit. Okay, and the reason for this is that in this particular case, with just identical particles, you get some cancellations that allow this to happen. But it's not true in general. So this is a bit slight detour, but this is not true in general. So if you have these exclusion processes, especially when you have like multiple species, or if you introduce angles, as we'll do in the second part of the talk, it is not true that if you do this mean field closure, you'll get the right result. And the sort of simplest case to see this, if you consider two species of particles, they are physically identical, but you tag them, you color them either blue or red. And here I'm even assuming, so we forget about the drift, so only the symmetric jumps, and the fusion coefficient is 1. So the hydrodynamic limit has this form here, so with this, again, this sort of gradient flow structure, as I showed before, with a nonlinear mobility matrix. So this is the crucial thing. So you get a nonlinear mobility matrix in the hydrodynamic limit. But if instead you did a mean field closure, you would actually get you would get the same free energy, but a different, a diagonal mobility matrix. Okay. Right. So if there are no questions here, I'll move on to the second part now, where we say, okay, now we want to use the same idea, but with basically to model active matter. Okay, and so as before, let's first just think what we want to do with just one of these particles. And the model that we'll consider is we have now, rather than like a circle, we have a triangle in each of these lattice points. So we model the positions as discrete on the lattice, but we allow for the orientation to be continuous. Okay, so we have a hybrid process where the orientation is a Brownian motion with rotational diffusion coefficient dr, and then the jump rates are basically what we had before, is now just that rather than having the asymmetric part being given by the gradient of a potential, we just look at basically the point of the triangle dotted with the direction in the lattice. Okay, so basically in this case here, the rate, the jump rates to go here or here are much higher than here or here. Okay, and so the idea of these rates, as before, is like if you take h to 0, you basically that's what you'll converge to. Right, so this is now just one, and of course what we want to do is put many of them. And as before, the exclusion, so we do this simple exclusion process, and the exclusion acts on both parts of the rate. Okay. And this is basically what Rob also mentioned, that was in Clément's PhD thesis. And it's much trickier if you have this exclusion also in the symmetric part. But basically you can do it. The idea now is that in the hydrodynamic limit, rather than having only a spatial density, so we'll have a density in position and orientations, and then we'll have basically the spatial density that tells us, okay, what's the sort of, where we don't care about the orientation, and then also like the magnetization here that tells us what's the mean orientation at a given macroscopic point X. Okay, and so I'm going to spare you from all the details here of Clément's thesis, but basically the hydrodynamic limit equation that he got. I mean, it's not quite this because in the work of James, we changed slightly the process in orientation, but basically the main idea here is exactly the same. So let me see. So now what you have is all these like nonlinearities here that arise from the fact that you're also excluding in the symmetric part, right? So this thing here is like the basically the symmetric part of the process, and this term here is the one that has this V naught in front, is the self-propulsion. So I mean, the only nice term here is really the angular diffusion. So this is what before was the switch between left and right movers. So now because we have a continuous change, so that's why we have this diffusion process here. But anyway, so all these other terms, note that they are, so this term here is, so this ds is the self-diffusion coefficient. So this is exactly the self-diffusion coefficient of a tagged particle if it was just doing a simple exclusion process. Okay. And then these other three terms depend on the self-diffusion coefficient. So if you know the self-diffusion coefficient, we have this hydrodynamic limit fully determined. Okay. The only issue is that we don't have like basically this involves solving a variational problem in infinite dimensional space, so you have to approximate this self-diffusion coefficient, but there are very good numerical approaches to do this, right? But the idea is that you need to get this, and then basically we have this PD all clear. And perhaps just to make a comment back onto the mean field approximation. So if you did mean field, then the approximation of this would just be 1 minus rho. Okay? And so if you now think what happens if you plug in 1 minus rho here, this becomes 1, and this becomes 0. Okay? So suddenly what it means is that so this term here just becomes this f grad rho, and this term here, is it this one? Yeah, this one here goes. Okay, so basically, in the self-propulsion term, you only have, I guess what you would expect from just having one particle, one active particle, but then with this reduction, 1 minus rho in the self-diffusion. Okay. So anyway, we have this PD that we have. So this is an exact. There is a theorem that says, okay, if you rescale the rates in the microscopic process in the appropriate way, this is what you get in the limit. Of course, what we want to do is to say like, well, we can then use this PD to capture phenomena like this. No? So this again, this motility induced phase separation. And now with these continuous orientations. Okay, and so sure enough, if we solve the PDE, we also get the same sort of patterns. And I guess also the important thing is if you imagine, so here that would be where the phase transition is. So you see this very strong magnetization across the sharp interface. Okay, so the sort of active particles are like pointing inwards towards the cluster to kind of lock it in position. Right. Okay, and so we can also look at both like linear stability and then through numerical simulations of the PDE to basically obtain this phase diagram. Or I forgot to put the axis here, but basically this is the density. And this thing here is the self-propulsion. And so basically, if you have very slow particles, the homogeneous state is stable. And as you increase the self-propulsion, then you cross into this region where you get MIMPs. And basically, we get nice agreement between the linear stability and what the numerics of this PD is telling us. Okay, so I'll show you now, well, we have these models of particles on a lattice where we just have passive particles, and then this model with active particles. And so kind of an obvious question is like, well, if we put these two together, what happens? And so the model that we considered for this is a slight simplification of the model in this second part, in the sense that rather than having a continuous orientation, we just fix it to be left or right movers. And so the active particles are now just like plus or minuses, where basically, so then they have this asymmetric or slight asymmetric rates, either like left or right, whereas the passive particles are just doing the simple symmetric exclusion process. Okay, and so basically, like it's relatively straightforward to extend the hydrodynamic limit for passive particles only to the case where you add these passive particles. The crucial point is that we need this dt, this coefficient here, to be the same as these ones. Okay? If they are not the same, that's not at all straightforward. But if we pick them the same, that's fine. And basically, we can again get a hydrodynamic system of equations for, in this case now, so we are denoting this rho 0 is the density of passive particles, and then these rho minus and rho plus are the left and right moving particles. And then I'm also defining now the total spatial density rho and the magnetization here, just rho plus minus rho minus. Okay, and so the hydrodynamic limit that we get has really the same structure as before. And so I guess the only thing to note is for the passive particles, we just put sigma 0 here. What you see is that, of course, they don't have this term here because that's the sort of their own self-propulsion, but they do get like I guess some sort of effective self-propulsion term due to the active passive particles around it. But note that if you do a mean field, you don't have this term. Okay, so if you did a mean field at this level, the coupling, I guess, would only occur through here, and then the fact that, there would be more crowding due to passive particles, but there would be no effective drift acting on these passive particles. And yeah, now in this case, rather than the rotational diffusion in here, we just have basically the tumbling rate, which of course it's only acting for the plus and the minus particles. Okay. So I'm just going to show you now some simulations, some PD simulations for this system to just show you a bit like the sort of things that can happen. The first thing I want to show you is that you also get these MIMPs in the mixture. Right, so basically we start with something that's a perturbation of the uniform state, and eventually you get this liquid cluster and some vapor, some gas in here. And again, note this profile where you have high concentration of left moving and right moving here, and then some uniform zero magnetization in the sort of middle. And this is just a plot of exactly the same simulation, but now comparing in the left particle simulations, and the right is this PD solution. Okay, so we get really nice agreement between the two, as we would expect, because we have a hydrodynamic limit. Okay. So what we did now with this system is also like do some phase diagrams. Here, instead of doing density against self-propulsion, what we plot here is the active fraction of particles versus the passive particles for a fixed self-repulsion. Okay, and this is the sort of diagram that we obtain that would correspond to the sort of simulations I showed you, where we have so this red curve here is the binodal curve that kind of traces the fractions of vapor and liquid phases. And then this binodal here is the limit of stability that let's see what with analogous of the curve I showed earlier for just the active particles. And yeah, so what we see is that basically for inside this blue curve, we get these phase separated solutions. In here, we can have both, and outside is only like where the homogeneous state is stable. And so what's interesting here, so for this binodal curve, we basically, this is just saying, okay, like what's the sort of pairs of densities that we have in each phase. So basically like just joining these 2 points here, it's telling us, okay, what's the fraction of active passive that we have in liquids or the vapor. And what's interesting as well is that for this system that's particularly, I guess, well, is amenable to the analysis, we could show that the way the solution moves along the interface, so if you just think of, I guess, here, so the way you move from the vapor to liquid follows exactly this line, which is called the tie line. Right? So it's not only telling us, okay, what are the fractions at the sort of when we have flat regions here, but also exactly how you interpolate from one to the other, which I think is quite cool. I don't know if it's that visual or not, but anyway. So this is the sort of I guess standard looking phase diagram. I think I should have said I have no physics background, so that's for me like that's just as cool as this one. But probably I'm told that this is not so interesting, whereas this one is interesting. And so what happens here is this in this system of mixtures, if I increase the self-propulsion or the Peclet number here, so it's a rescale self-propulsion, then basically suddenly this spinodal protrudes or pokes out of the binodal. Okay, and then, well, if this happens, then you need to come up with a new color to paint this phase diagram, and in this new color, it's where basically like you expect some new interesting physics to occur.
So the gray region, is that arrested?
The gray region is because basically the sum of the two has to be, it cannot go higher than 1. Yes.
But should you see an arrested phase?
What does it mean arrested?
I mean, like in, I guess, like also Rob showed, right? If you have phase separated, if you go too high density, which is, well, phi A is not density, right?
Phi, yeah.
What's the ratio of passive to active?
No. This is not the ratio. This is just so basically like that's just the volume fraction of actives.
So if that goes really high, at some point they should jump.
I mean, yeah, basically in this case here, if you are here, then they completely jump. Yeah, so your lattice is completely full. But yeah, I guess we didn't really explore too close to that region.
It should be able to very fast. I believe.
I mean,
it is.
well, yeah, I mean, basically you have this self-diffusion coefficient that goes to.
It is a function of the density.
Yeah, exactly. So. Okay. Anyway, so I'm now with the time left. I'm going to show you some examples of what goes on in this blue region that we labeled as D. So one example of solutions that we get is what we call this counter-propagating. So here we start again with the PD with some perturbation of the homogeneous state, and yeah, if we write for long enough, that's the sort of things that happens. So it's something that it looks like you are getting into like a meme solution, but suddenly the two interfaces get closer and then they pass each other. Okay, and so this is through like numerical well, analysis of this PD, but it seems that it's a sort of repeating pattern that doesn't. It's not as if then it's going to end up anywhere else. And so this is same as before. So here we have the particles and the PD simulation, and we get there's like nice agreement between the two. Okay, and then another type of solutions that we could also find in this system is what we have where we have this traveling solution. So the idea here now is that we have so if you look at the black curve, so that's the total density. So we have basically like a front here, that's an interface between dilute and dense regions that moves in just one direction. So if you like, it's as if you took the counterpropagating, but you only had one side, one of them. Okay, and so this is again the simulation in time, and you see that originally there is some perturbation. It seems that you get this two counterpropagating, but then I guess through one of these clashes, one side ends up dominating, and then you just get this nice thing moving at a constant speed. So for this one, I guess I don't have time to go into the details, but we could do some further analysis to characterize exactly what this interface looks like. And what was really cool is that we were able to say that the actual interface, even if it's moving when you move to traveling coordinates, it's like the same as MIMS. So basically the tie lines I was showing in the phase diagram, that predicts how this interface looks. Okay, and so for instance, this is just some example of how this sort of analysis looks on the phase diagram. And so just to show as well, so I guess we were then investigating the multi-stability in this of this system. In particular, looking at, depending on the sort of initial perturbations, what sort of solutions we observe. So the one on the left here is where we perturb with some left and right modes. And in this case, we only get this, in this region, we only get this blue counterpropagating dot. Whereas if we introduce only like a left traveling mode, then we got some of these T solutions, these traveling solutions, but then some of them ended up becoming counterpropagating as well. Okay, and so just to put this into a context of, I guess, other systems that have been appearing recently. So we think that this model of active and passive mixture is an example, or at least the sort of physics that we observe is similar to these non-reciprocal interaction systems, although only like in an effective way. So here the particles microscopically, it's not that we introduced any non-reciprocity, but when we sort of coarse grain, we basically have the fact that adding these diffusive particles introduces some sort of non-reciprocity that leads to these dynamical states. And here I just wanted to mention that the sort of canonical model to study these things is where you just take this Cahn-Hilliard system and then you couple them through some cross diffusion terms. If you make this cross diffusion terms different, then that's kind of how they introduce this non-reciprocity in this paper here in the group of Marchetti. Basically we're still, I mean, in this model, of course, of ours, like it's only emerging as some effective interactions, and it's not really in the symmetric part of the jumps, but in the self-propulsion. But we think it's a good way of understanding some of the physics that we're observing. So just to summarize, I've showed you how we can use these simple exclusion processes to model interactions in passive and active systems. So for passive particles, basically like you have a hydrodynamic equation where basically nothing exciting happens, it's just equilibrium physics. With active particles, you basically get a hydrodynamic limit that captures very well this mobility-induced phase separation. And then basically, yeah, when you add something boring to something a bit interesting, then you get something even more interesting in this sort of spirit of perhaps Turing patterns. Yeah. Okay. Thanks for your attention.
Thanks for the very nice talk. We've maybe got time for a quick question or two while Thibaut sets up. I forgot to mention also the online participants, feel free to ask questions in the Zoom chat or put your hand up if you do have a question. Yeah. Oh, there, sorry.
Okay, is there some physical explanation why the mobility matrix is diagonal in the mean field approximation and not diagonal without in the exact limits?
I mean, I don't know, I guess the mean field wouldn't be a physical approximation, so I'm not sure how to, in that context. So I mean, I think you have some, correlations in the simple exclusion process that are not decaying fast enough, but yeah.
Anything else? I also had a really quick question. Is there any remnant effects of the activity if you take the limit of rho plus or minus going to 0? Can you get back to the passive limit? It might be a stupid question, but sometimes I know that activity can sort of leave
no, in this one for sure, yeah. So if you take the you get so if you take this one, you recover what you the sort of model I showed in the first part, yeah. Yes.
I think, yeah.